Welcome to our video covering the distance formula, and here we're going to be looking at not only how to apply the distance formula, but to understand why we write it the way that we do. So what is the distance formula? Well, before we get there, let's talk about the step we need to understand that's in between distance and the formula itself, and that's the Pythagorean theorem. The Pythagorean theorem is, I think, the key to understanding our distance formula. And that theorem, if you haven't seen it before, it says that a squared plus b squared is equal to c squared. So what's the connection here? And if we're talking about distance, how does the Pythagorean theorem come into play? Well, typically what you're shown is a point on a grid. So let's say that we have this point right here. And we can call that point A. And that's 1, 2, 3, 1, 2. So it's 3, 2. And then we connect it to another point on the grid. Let's say, I don't know, how about this point right here? We'll call that B. And this point is 3, 4, 5, 6, 1, 2, 3, 4, 5. So it's 6, right? And then 5. Okay. The question often arises is how far apart are these two things? In other words, how far is this line right here? That's the distance between them. Well, without actually taking out a ruler, how do we do it? Well, that's where the Pythagorean theorem comes into play. So we have the x-axis and the y-axis, right? So let's say that if I use, I don't know, this color right here, that's my x-axis. Pretty close to the other one. Let me fix that. So this is our x-axis. And here, these 2 points, the first thing we ask is, well, how far apart are they on the x-axis? So we draw a line like this along the x-axis. And then we say, well, what about this vertical height? How far are they vertically from each other? Well, then we look at the y-axis distance right here. So we draw another line. And this shape that we form when we do this is a right triangle. And the Pythagorean theorem comes into play. So that's exciting, right? Because a squared and b squared, well, that says basically if you take side A, which is right here, this is side A, and you look at side B and you square that, this is side B, the square of those two sides has to always equal the square of side C, the hypotenuse. And that's the distance that we're looking for here. So, in a squared and b squared equals c squared. So let's get to it. How far apart are these 2 points? Well, let's use the Pythagorean theorem. How far apart are b and a? Well, let's write them over here, right? We have b, which is 6, 5, and a, which is 3, 2. Well, how far apart are they on the x-axis? Well, that's the a distance, first of all. So that's the x distance. I'm going to compare these two values. How do you find how far 2 points are on a line like that? Well, you subtract, right? So the x distance, right? Let's write x distance is equal to 6 minus 3, or 3. And you can see that, right? A is 1, 2, 3. And the y distance, and that's our b value here, is what? Well, we go up 1, 2, 3, but you can just subtract the y values to get that. So 5 minus 2 is 3. So the x distance and the y distance are both equal to 3. And just to be clear, this is equals a, right? That's our a value of the triangle, and this equals b. So now we can label this up here. A equals 3, and bear with me, b equals 3. What does c equal? Well, now that we have these two numbers, it's easy, right? Because we just plug into the formula. So what we do is we take a squared, which is 3 squared, add it to b squared, also 3 squared, and we get 9 plus 9, or 18. So c squared equals 18. But we don't want to know what c squared is. That's a square, right, off this side. We don't want to know that. We want to know how long this line is right here. So we take the square root of both sides. Square root of c squared and the square root of 18. Well, the square root of c squared is just c, right? The square root of anything squared is just the number itself, which is a nice thing to use in a problem like this. And then you could almost stop here, the square root of 18, but you can split it up a little bit further by realizing that 18 is really 9 times 2, And you might know this part. We can take the square root of a factor here. So the square root of 9 is 3. And c equals, well, the square root of 9 is 3, so that comes out of the radical. And then radical 2. So this is a little interesting. These 2 points are about 3 radical 2 apart. It's not a rational number. And that makes sense, so we'll come back and talk about that in a second. But about how far is this distance? Let's just estimate. Well, what's the square root of 2, right? What is the square root of 2 about? It's about 1.4, 1.41. So we could say this is about 1.4, right? Let's say 4142. That's about the square root of 2 times 3. So it's about 4.2426. We'll say 4.24. And if you look at that makes sense, right? Because the hypotenuse should be, on the triangle, should be a little bit longer than the legs. But your instinct is almost to say, well, it should be 3 because it goes across. If you look at this line, I'll just redraw this line over here. It goes across 1, 2, 3 squares. But if you think about a square in itself, and this is a fun thing to think about, that line's not 3, just because it goes across 3 squares. It's a little background with the Pythagorean Theorem. When you go up across a diagonal like this, if each square is a length of 1, which they do here, these are right dashes 1 and 2 and 3, and going up it's 1 and 2 and 3. Well, how far across is this length right here? Well, the Pythagorean theorem comes into play again. 1 squared plus 1 squared is 2, so c squared equals 2, but c equals the square root of 2. So every time you go across a square where each side length is 1, that distance is the square root of 2. So in this case, this line is 3 square roots of 2, which is what you're getting here. And I just wanted to throw that out there because often for the distance formula we don't get whole numbers. And in fact, we often don't get rational numbers. Part of the reason of why that's happening is because the diagonal here, these hypotenuses, are not rational numbers themselves. This is based on one fundamental idea in the Pythagorean theorem. We could get stuck with a lot of approximations. So I want you to understand that. But anyway, our goal here is to look at the distance formula. How are we going to get there? Well, if we kind of model the process that we just did, but with algebra, we can see where the distance formula comes into play. So let's say c squared, right? We're trying to solve that. C squared equals a squared plus b squared. That's what the Pythagorean theorem says. Well, if I'm solving for c squared, and I was just working from here, what I would do is what? Well, I would take the square root of both sides. So square root of c squared equals the square root of a squared plus b squared, which is exactly what I did here, right? I added up a squared and b squared, and I got 18, right? A squared plus b squared, here it is, equals 18. And then I took the square root of that. This is all in one package that I'm saying right here. Now, when I did that, right, the square root of c squared is just c. So that equals, right, the square root of a squared plus b squared. This is the distance formula, right? It tells you that the distance you're looking for, which is this diagonal, is equal to the square root of the sum of the two sides squared. Wow. But this is not often how you see it, because what comes into play next is this little thing, right? These little equations right here. How do we find a and b? Well, what we did was, right, if you look at the coordinates, let's say this is x, right, 2 and y 2. So it's the second x and y because we had points a and b, and this is the first x and y. To find our x distance, that was our a value, we subtracted our two x coordinates, 6 and 3. In other words, we subtracted x1 from x2. So I can start rewriting this. C equals, here we go, x2 minus x1. That's just our a value, right? I just subtracted that and found the x distance here. That's squared. Plus, well, for the b distance, we subtracted, that was our y distance, we subtracted y2 minus y1. We found that height. So by doing that, I get this. And this is our distance formula. Only we often don't write c, we write d. And all it's telling you is to subtract the two x values and the points you're comparing and square that. And then subtract the two y points, right, that you're comparing and square that. Add these up and take the square root, and you've got the distance. And you don't have to memorize this because really all you're doing is finding the hypotenuse, right? That's between these 2 points here. Sometimes you get vertical points and then like 2 points above like this. In that case, right, just count the distance between. It's just much simpler. Go 1 and 2 and 3. But we can still apply our distance formula. Because then what will happen? Well, let's look at this one. We get -1, -2, -3, -4, -5, and then down 2. It's -5, -2. This is -5, -3, 4, 5. Applying our distance formula to find the x distances, we just subtract these two. So -5 minus -5, which is 0, squared, which is 0, plus, well, -2 minus -5, which is 3. Right? -2 minus -5 is 3. Subtracting those y ordinates right there. Are they called ordinates? I forget. Anyway, so y2 minus y1 squared, which is 9. And we take the square root of that, this distance formula. Square root of 9, that's 3. So you can always apply this distance formula, but sometimes just be aware it's much easier just to count the distance between 2 points. But when you get these diagonals, it's not always so easy to count. Sometimes you get a number of square roots of 2, like we did here, but not always. It depends how it cuts across the squares. Anyway, I hope this helped. In the next video, we'll look at some other application problems. All right, thanks.